This meeting is being recorded.
Okay. So today's speaker is Benjamin Dünzinger, and his talk, you can see it behind him, Categorified Assembly, and his own work with Georg Lehner. Please, then go ahead.
Thanks a lot for having me. Yeah, so let's start a bit with the setup. So in this talk, G is always gonna be a group. I mean, most technically would work for even groups in spaces. So, but we'll fix a group in sets. So if I don't mention anything otherwise, everything is gonna be homotopical, so higher categorical in this talk. And we also let R be a ring spectrum. Then sort of classical object that is considered is the assembly map for the group ring. Namely, we can compare the K-theory of the group ring with this co-limit indexed over Bg of K-theory of the ring. And between those two objects, we have an assembly map. And the classical point of view is that this right-hand side should be viewed as an interesting invariant of G, or depending on taste, maybe Bg. And this left-hand side should be seen as a first approximation of the right-hand side. Okay. And it's interesting to study these kinds of maps. And one question one can ask about this map is this assembly map split injective? Okay, so maybe first remark, this is a well-studied question. Namely, this is known under many group geometrical assumptions. Here, let me mention a couple of important steps in this. So a first step was by Carlsson-Pedersen, and then Arthur Bartels proved this under the assumption of finite asymptotic dimension for G, and Ramres de Sierra you proved this under a notion called finite decomposition complexity. So in all, this is known under many in many cases, and maybe to mention it at the beginning, due to this, there won't be any new examples in this talk. But to explain what else is going to happen, let me give some context. Namely, one can study the same question in the context of operator algebraic K-theory. Okay, in this context, one has an assembly map from the topological K-theory of the complex number to also a group ring, but in this case, one takes an appropriately completed group ring called reduced cross product. Okay. And in this context, there exists the following strategy to prove a split injectivity result. Namely, one can note that one actually has a large composition of functors as follows. So one can start with these algebras with G action. So here, such that this actually is well defined. In this situation, G is going to be countable. And so one can look at G-C-star algebras, and then one has a variant for these called equivariant KK theory. And from equivariant KK theory, one also has this reduced cross product functor to usual KK theory. And topological K theory just as a functor from KK to spectra, at least as I want to view it. And because one has the sequence of functors, one can prove that this assembly map is split injective using the following idea, essentially due to Kasparov. Namely, this idea is just find an element gamma in the equivariant KK group that is idempotent such that this idempotent induces the splitting we are looking for. So namely the splitting colimit BG K top of C plus some remainder term is equivalent to K theory of the reduced cross product. And this decomposition on the left-hand side should be induced by the class that gamma induces in KK or in spectra. So let's call this induced by gamma lower star. Okay. So this is a potential method of proving split injectivity results that works very often in this operator algebraic context. And what I want to ask in this talk is, does this strategy also work in the context of algebraic K theory? Okay, so what does this mean? This means, first of all, we want to find a replacement of this category KKG in the algebraic setup. Then we want to find a nice description of gamma elements inducing such a decomposition, and then finally provide a couple of examples where such gamma elements actually exist. Okay. So let me next talk a little bit about the setup of algebraic K theory I want to use for this. So more or less most classically, algebraic K theory is an invariant for unital rings. So here algebraic K theory is always going to be a non-connective K theory. And a standard approach in the last couple of years was to not view K theory as defined on rings, but rather on some kind of categories. And the precise categories one uses usually are idempotent complete stable categories. And more recently, this domain for K theory has been extended to so-called dualizable categories by Efimov. So Efimov observed that one also can define a K-theory functor on this larger domain, such that on things coming from here, it still gives the same K-theory. So these dualizable categories inherently are sort of a little bit higher categorically technical, but for completeness sake, let me give a definition. So what is this? So these dualizable categories one can most conveniently describe as a full subcategory of something called PRLL stable. Okay, so let's first say what the objects are. The objects are objects that are dualizable in PRL stable. Okay, so this PRL stable is just a nice notion of co-complete stable categories. And Lurie observed that this category has a tensor product. And dualizable literally means dualizable with respect to the tensor product on this category. And this LL refers to, so usually functors in here are colimit preserving functors or equivalently left adjoints. And this double L refers to that we take as functors those that are sort of twice left adjoint, meaning that every map actually is a triple. So we have a functor f lower shriek. This functor has a right adjoint, typically noted something like f upper star. But so this would be a map in pure L, but the double L refers to the fact that this f upper star is again a left adjoint, meaning it has a further right adjoint. Okay, so technically this is the precise setup, but what's actually a little bit more important for us are the examples. Okay, so the first example is for any ring spectrum. We can consider modules over this ring spectrum. And this category is dualizable. And furthermore, its K-theory is the same thing as the K-theory of R. Okay, so this means that in this dualizable context, the classical examples coming from rings have the name mod R. Okay. Second example is, and that's actually the reason why I want to work in this bigger context, is for X a locally compact Hausdorff space. Also, sheaves on X is dualizable. So here in this talk, whenever I write sheaves, I mean sheaves with values in spectra, just because somewhere in here the categories are stable. This is dualizable, and furthermore, one can even compute its K-theory. Namely, a result of Efimov is that the K-theory of this sheaf category is just the same thing as compactly supported homology of X with coefficients in K-theory of the sphere. And this is really a new example in the sense that usually sheaf X is not in the essential image of this functor. And that's sort of the reason why I want to work in this setup. And sort of for completeness, to give a more concrete perspective on these dualizable objects, let me also mention that a general dualizable category actually has the following form, namely it's the fiber of a map between modular categories of rings where this map is induced by tensoring with a bimodule and we furthermore also want that this tensoring with this bimodule is even left Bowes field localization. Okay, so this is a very concrete point of view on this condition. Okay. Now, the next goal is to construct the analog of equivariant KK theory. So for this, let's take a space. So usually X is just going to be BG for our group G. And just as notation, we'll denote X-indexed systems of dualizable categories with this symbol. And an X-indexed system of dualizable categories is just a functor from X to dualizable categories. And also just as terminology, a bifiber sequence just means, so to speak about bifiber sequences, we first fix a pointed category, meaning a category with 0 objects. A 0 object is just an object that is simultaneously initial and final. And in such a category, a square, where this is the 0 object, is a bifiber sequence. If it is simultaneously pullback and push out. Okay, so the reason why I introduced this is just that K-theory and more general, the invariants we want to consider are precisely those that interact nicely with this structure. So our analog for KK theory is going to be the category of localizing motifs, and we'll use essentially the definition of Bloomberg, Gepner, Taboada. And so what is this localizing motives thing? It's a universal invariant for X systems of dualizable categories, meaning it's a functor from these X systems of dualizable categories to some other category called mod of X, such that, so first of all, we want that U preserves filter colimits. And precisely bifiber sequences. So maybe note that dualizable categories are a pointed category just with a zero object given by the zero category. So we want that U interacts nicely with filter colimits and these bifiber sequence in here. And furthermore, U should sort of be the initial functor that is compatible with the structure, meaning that for all stable categories, we have that a functor out of mod X to T that preserves colimits is the same thing as a functor from these X systems to T that preserves filtered colimits and bifiber sequences. Okay. So this is a definition of the via universal property of the category of X motives and the universal X localizing invariant. Of course, one has to construct this category. One can do this similar to, for this one can use what Bloomberg, Ebner, Tabuada do, for example. There are also other ways. So, remark. So this the main player for us is going to be mod of BG, which we'll also just abbreviate by mod to the G. And this should be seen as analogous to equivariant KK theory. And so for this reason, also following Efimov, we'll denote the mapping spectrum in these G motives by KKG of A to B. Okay, so this notation has, for example, the advantage that we have KK of the point from the unit, which is spectra, to something arbitrary, is the same thing as K theory of A. This is due to Lamberg and Tabuada. Okay, so this accomplishes the first step. For us, it's gonna be important to understand how these G motives categories interact with each other if we vary G. So more generally, we can start with a map of spaces And then we have on the level of systems of dualizable categories the following operations. Namely, given something indexed on y, we can pull it back to something indexed on x. And also, we have a push-forward operation. So note that these are just functor categories, and therefore, and because this is co-complete, we have a left Kahn extension, which I denote by f lower shriek. So slightly informally, this f lower shriek applied to some a can be computed as, so this is something varying over y. And so Kahn extension just means that I take a bunch of colimits and at position y, take a colimit over the fiber of y. So this is a short notation for the homotopy fiber of small y under f of a. Okay. And now the relevant point for us is that these two operations directly descend to motifs. Okay, one can, for example, deduce this directly from this universal property via showing that, for example, if I restrict my system, then I apply U, that this functor preserves filter colimits and bifiber sequences. So also on the level of motifs, we have these operations. And next, let's see what these operations are in an example. So for example, I can consider the base point inclusion of Peachy and apply this shriek operation to some u of a. And then this is nothing else than u of the induced category, as one maybe would expect. So with this operation, one can express induction. And so another interesting map we have is just a map from BG to the point. And also in this case, we can apply this lower shriek to some u of a. So here, this a is in here dualizable of BG. And here we have, if one looks at this formula for f lower shriek, that is the same thing as u of colimit indexed by BG of a. Okay, so these colimits in the context of these dualizable categories can sometimes be a little bit confusing to calculate. But so in the most explicit case, where we take A to be mod R with trivial G action, we can compute this as U of functors from BG to mod R, which is the same thing as U of the group ring. So in this sense, one can, using this operation, express the invariant associated to the group ring. Okay, so this is our analog for the category KK. So the next goal is to understand what it means to have an analog of this gamma element in this context. Okay, so notation is I want to write mod to the HG just for the category of motives with G action. Okay. So this notation maybe suggests that this is some homotopy limit of some sort, and this is actually also correct. So this is also the same thing as the limit over BG in PRL over the trivial action of mod. But because of some surprising behavior of this category PRL, this is also the same thing as the co-limit index by BG over PRL mod. So these two equations are not very important for us. It's just I just want to point them out to justify why what I will mention the following is called assembly. This is the important definition. Okay, so the categorical co-assembly map is the following. So it's a map from a gadget attached to G, in our case mod G, to a gadget associated to some limit, in our context mod to the HG, and this map will be called RS upper star. And how does it work? So recall that this defining a map out of this usually is the same thing as defining an appropriate map out of this category. And this map here just is, we can take a category A and we can associate to it its motive. And then recall that this motive still had a G action, and therefore we actually obtain an element in this category. And this is going to be our categorical co-assembly map. Okay. There also exists a categorical assembly map. And this is a map from this mod to the HG. But recall that this is just, can also see this as a co-limit indexed by BG over of mod, where the action here is trivial. And just using the co-limit exchange map, for this lower Schrieg functoriality we had before, we obtain a map to mod of co-limit BG of point. And this thing here is just BG. And therefore, we have a map to mod to the G. Okay. And lastly, the sort of assembly map in this context is the following. Namely, the motivic assembly map is for A in a dualizable category with G action is a map from co-limit BG U of A to U of co-limit BG of A. And maybe recall that this is nothing else than BG lower Schrieg of U of A. Okay. So these are sort of three variants of assembly we have in this context. So maybe the first and the second one really try to compare this complicated category with this a little bit easier to handle category, because the equivariance data involved is just homotopy theoretic. Okay, so this, especially this categorical assembly map, maybe is a priori not completely clear how to understand this, but this is made clear by the following result. Namely, this map, so I call this map also I lower Schrieg, because it's constructed using this Schrieg functoriality. The map I Schrieg is actually fully faithful, tensor ideal, and its essential image is given by the co-limit closure of our induction functor. Of the essential image of the induction functor. So in this sense, this category in here precisely describes everything we can in principle understand using induced objects. Okay. So next step is to characterize the main properties of this gamma element, which we need to obtain an appropriate splitting. So this and related notions are captured by the following definition or proposition. So we say that G satisfies a strong split injectivity if one of the following equivalent conditions hold. Okay, so the first one is, so we already had that this category here sits fully faithfully inside mod G. And our first condition is that this category actually splits as a direct sum into this mod HG plus something else, such that the obvious triangle here commutes. The second, for the second condition, let me clean the board. The second condition is there exists some gamma, an endomorphism of the unit in GeNoCAS, such that if we apply this RS upper star to gamma, then we obtain the identity. And this gamma also should factorize over something which is essentially induced, meaning there exists a factorization over something where this question mark should be in the essential image of this RS Schwick functor, meaning in the colimit closure of induced object. And this composite should be the same thing as gamma. Okay. And the third condition is convenient reformulation of the second one. Namely, there exists an element F, which is a map from U of spectra to some A for A induced and such that RS upper star of F is an equivalence. Okay. So this definition is a proposal for an analog of the Dirac-Dirac method in the context of algebraic K-theory. Okay, so maybe first a remark. So if G satisfies strong split injectivity, then in particular this motivic assembly map for all categories A is split injective. So in this sense, this is strengthening of split injectivity with all coefficients. And now maybe to the most interesting part, whether there exist examples of groups satisfying this condition. So the first example is the integers do satisfy this condition. Okay, so the basic idea is to use these sheaf categories to build such a gamma element, or more precisely, such an element F. Okay, so how does this go? One can consider the following exact sequence. So one can take sheaves on the real line, and this includes into sheaves on the real line with a point added at -infinity. In such a sheaf, I can restrict to a sheaf on -infinity, aka to spectra. Okay, so a standard excision result with respect to the sheaf categories tells us that the sequence without the use is actually a bifiber sequence in dualizable categories, and therefore I get such a exact sequence in motives. But there's not only an exact sequence in motives, even an exact sequence in motives with integer action. Here I just act by a shift, here as well, and I leave this point fixed, and here act trivially. So this is a fiber sequence in set motives. Okay, and maybe let's also look at the boundary map here. And let's call this F. And now an observation due to Efimov is that this category actually vanishes, or the motive of this category vanishes after we apply IS upper star. So we have IS upper star of U of sheaves of R and -infinity is 0. And this actually implies that this F satisfies condition 3. Why is this the case? So the point is that this sheaves satisfies sort of open-closed excision, and we have a finite free set CW model structure of the real numbers, of course. And therefore, this thing here is essentially induced. Therefore, the same is, of course, true here. And therefore, it suffices to check that this F is an equivalence after applying IS upper star, but this follows from this equation here. And maybe a justification for this equation is Efimov has shown that U of a sheaf category is actually the same thing as an appropriate version of compactly supported cohomology. So with respect to K-theory, I already mentioned this at the beginning, but this also works with more general coefficients, and one can observe that this is 0. Okay, so this shows that there is at least one example. So let me mention two more things maybe. So first, one sort of should view this strong split injectivity as a version of split injectivity which has better inheritance properties than classical split injectivity. This is a consequence of the following result. Namely, strong split injectivity is closed under extensions, subgroups, and filtered colimits along inclusions. All three properties are non-obvious if you for just split injectivity, as far as I can see. And maybe lastly, let me mention our sort of biggest class of examples, namely groups satisfying the conditions of Carlsson-Pedersen. If you're interested in more details, I can go into this after the talk. Satisfy strong split injectivity. Yeah. So, yeah, that's it.
Okay, so that's it. The end of your talk.
Yes.
Okay. Okay, so thank you for the talk. Are there questions from the audience?
I have some.
Yeah, please go ahead. Deb.
Okay, let me maybe start with like where you ended. So I don't know if Carlsson-Pedersen covers free products of group. Is this part of the inheritance property of strong split injectivity?
That's not part of the inheritance property yet, but it's covered by Carlsson-Pedersen.
Okay, I see.
So one thing that is open with respect to the inheritance property is whether the class of groups satisfying this is closed under amalgamated free products. And
Right.
yeah.
Right.
One little question. Do groups satisfying the Farrell-Jones conjecture automatically satisfy the splitting?
Yes.
So,
so
for example, hyperbolic groups, do they satisfy this?
yes, but this relies on, as of yet, unpublished results of Efimov, and it's not obvious. Yeah. But it should be true.
Okay, maybe some like basic questions. So is your mot G a rigid category? So mot is it automatic from there that mot G is also rigid?
It's not rigid, I think. Efimov has a theorem in a paper, but not without proof as of yet, that it's dualizable and it's self-dual. So the dual of mod G is again mod G. He has a statement for more. So I mean, mod G1 also can see as motives relative to a base ring, and the base ring is sort of an appropriate version of the group ring. So somehow this. And FMOF more generally has such a statement for motives relative to some base. The point is that this base is in generally only an E1 ring, right?
Right. Okay, and what is the bootstrap class of this mod G known?
This is related to the Farrell-Jones conjecture. I mean, so I mean, there are two problems. So first of all, the unit is not compact. Therefore, or at least I don't know why it should be compact.
Is it
this
omega 1 compact?
I don't know, probably. So this is the first obstacle if you just want to use results of the form that bootstrap equals modules over endomorphism of the tensor unit. Okay, so this might be wrong in this case. But furthermore, one can wonder what is endomorphisms of spectra in mod G. So one could ask what is KKG of spectra to spectra. And this one can, for example, re-express as K of BG lower Schwieg, just using adjunction nonsense, of spectra to spectra. And recall that this is mod of the group ring. Yes. Okay. And sort of calculating this object in motives involves the Farrell-Jones, a motivic version of the Farrell-Jones conjecture.
Right.
But if you assume this motivic version of the Farrell-Jones conjecture, which follows from Farrell-Jones with all coefficients in an appropriate way, then one has a formula for this thing as a limit over the virtually cyclic orbit category.
Okay.
So are you done, Deb?
No, I want to just end with like maybe a more imprecise question. So do you have some analog of E theory in this motivic world?
So what's the feature of E theory you're most interested for this? So you would actually be interested in an invariant which on a level of rings satisfies excision?
Yeah.
Then I don't have one. Yeah.
Okay. Is there any other way you can make sense of E theory? So maybe for me, a more tangential question about E theory is that I know that this shape functor classifies a C-star algebra up to asymptotic equivalences. Is there some notion of a shape functor for these dualizable categories?
That's to me a very interesting question. I haven't thought enough about it. But yeah, it sounds like a very interesting question whether using these sheaf categories one maybe can build something analogous to the category of asymptotic morphisms, but also seems not easy.
Okay, thanks.
Are there any further questions from the audience? Otherwise, I'll thank Benji again and stop the recording.